Hello, my name is Hardemon-Pace, and this is Group 14's Critical Design Review for our Project Scout, the Smart Cargo Operating Unit with Tethering. Our team consists of myself, Hardemon-Pace, Computer Engineering, Kaylana Brooks, Computer Engineering, Sam Orozco, Electrical Engineering, and Devani Trent, Electrical Engineering. So the reason we chose Scout comes down to a real problem. Warehouse workers spend their entire shifts pushing and pulling heavy carts, and that causes a lot of injuries. The BLS reported over 184,000 transport worker injuries in a single year. That number is way too hard and way too big to ignore. The existing solutions are either fully manual or fully autonomous. The autonomous ones work great, but they cost anywhere from $30,000 to $200,000 per unit. Most warehouses, especially smaller ones, can't justify that price. On top of that, those systems need you to modify the facility just to get them running. We wanted something in between. Scout follows a worker using ultra-wideband positioning, so the worker just walks normally and the cart keeps up. No infrastructure changes needed. Our target budget is under $400, and we're going for plus or minus 10 centimeters of positioning accuracy. That level of accuracy is what we need to make the following behavior actually smooth and reliable from Scout. We broke our goals into 3 tiers: basic, advanced, and stretch goals. The basic goal is the autonomous following. The cart tracks a worker carrying a UWB tag and stays at least 1 meter behind them. The objective behind that is getting UWB ranging reliable enough and fast enough to support smooth motion. The advanced goal is load sensing speed control. We have a load cell under the cart bed that reads the payload weight in real time. The system uses that data to automatically limit the motor speed when the cart is carrying more weight. The objective there is a closed-loop motor control system with smooth acceleration and deceleration built in it. The stretch goal is regenerative braking, where the system recovers some energy back into the battery system during deceleration. The power delivery work we've done so far sets that up, even if it doesn't make it into the final demo. Here are the key specs we designed the system around. The cart maintains at least a 1 meter following distance behind the worker and has a max speed of 1.5 meters per second. One of the things we're proud of is the load-based speed scaling. When the cart is carrying more weight, the system automatically brings the speed down to keep things safe. On the obstacle side, the cart detects anything within 2 meters in front of it and has to respond within 200 milliseconds. We also designed for a 15-pound payload capacity and up to 2 hours of continuous runtime on a single charge. For the final demo, we're focused on showing 3 things. First, the cart maintaining following distance using UWB tracking. Second, the speed automatically adjusting based on how much weight is on the cart. And third, the 15-pound capacity within the live weight readout showing on the LCD in real time. This slide breaks down the specs at the individual component level. Starting with the UWB modules, they need to hit plus or minus 10 centimeters of positioning accuracy at a minimum update rate of 10 Hz, and they communicate with the ESP32 over SPI. The battery is a 24-volt lithium-ion pack with at least 10 amp hours of capacity. It also needs to handle peak discharge above 50 amps since the motors pull a lot of current. The BMS, the battery management system, sits on top of that and monitors each cell individually, protecting against overcharge, overdischarge, and short circuit. For the load cell, we need a measurement range of 0 to 30 pounds with a resolution of 0.1 kilograms, which gives us enough precision for the speed scaling to work accurately. And for the motor drive subsystem, it runs at 24 volts DC with a continuous current rating of 20 amps and a peak of 40 amps to handle the startup and load demands of the motors.
Next is the hardware selection and design. This section covers the decisions we made around our microcontroller, our UWB localization modules, and the drive system. So for our microcontroller, we evaluated 3 options: the Arduino Mega 2560, the Raspberry Pi 4, and the ESP32. So looking at the Arduino, we knew that this was already very limited. It has an 8-bit processor with no real-time operating system support. So this ruled it out for the kind of concurrent tasks scheduling our project requires. Next, going to the Raspberry Pi 4, although it is powerful, it does run on Linux, which introduces unpredictable latency, which isn't acceptable for our project. And it also draws significantly more power compared to the other microcontrollers. And lastly, looking at the ESP32, it runs FreeRTOS natively, giving us true real-time control. And it also has enough GPIO pins to interface with all of our peripherals. And it has a low cost of about $10. And our team has had prior experience with the ESP32 from other coursework, so this was a clear fit for us. Next, we will go into our ultra wideband modules. So we compared against 3 different modules: the ESP32 UWB DW1000, the DW3000, and the MA UWB ESP32S3 module. So all 3 of the modules hit our plus or minus 10 centimeter accuracy target, and they also operate at a low power over a 50 plus meter range. So the true differences came down to the features and costs. So the DW3000 offers lower power draw and Apple device compatibility, neither of which we need. Next, going on to the MAUWB module, it does have better native multi-anchor support and a longer range of 300 meters, but it has a higher cost of $54.80 compared to the DW1000, which has a cost of $39.80. So the trade-off is that the DW1000 doesn't natively support multi-anchor trilateration, so we decided to go with the DW1000 and just implement the trilateration math ourselves in the software. Now that was our original line of thinking. However, after purchasing our PCBs and searching for the components for it, we realized that the DW1000 is very low in supply. That's very hard to acquire for our project. So we moved over to a DW3000, and we will be using that going forward.
Hello, my name is Devani Trent, and I am responsible for the hardware design of our motor control system. My contribution focused on selecting, designing, and implementing the motor driver hardware that powers the 2 drive motors used in our Scout platform. One of the most important hardware decisions was selecting the motor driver architecture. Since our system uses 2 24-volt, 250-watt wheelchair motors, we needed a solution capable of handling high current while maintaining efficiency and reliability. As shown in this comparison table, I evaluated 3 different approaches: an integrated H-bridge motor driver IC, a half-bridge gate driver solution, and a DRV8701 gate driver paired with an external MOSFET full H-bridge. Integrated H-bridge solutions are simple to implement because the driver and MOSFETs are packaged together in a single chip. However, they are limited by the thermal and current capabilities of the IC package, which can become a concern when driving larger motors. A half-bridge solution offers high current capability but requires 2 half-bridge stages and additional design complexity. The option we selected was the DRV8701 with external CSD19536 KTT MOSFETs configured as a full H-bridge. This approach gave us the greatest flexibility because the current capability is determined primarily by the MOSFETs we chose, rather than the driver itself. The external MOSFET design also provides lower on resistance, better efficiency, and improved thermal performance. In addition, the full H-bridge allows us to drive the motor forward, reverse, and at variable speeds using PWM control from the ESP32. Overall, this architecture provided the best balance between performance, scalability, and engineering complexity for our project requirements. Here is our hardware block diagram, which shows how all of the hardware subsystems interact within the overall system. At the center of the design is the ESP32 microcontroller, which acts as the primary controller for the platform. The ESP32 generates PWM and direction signals that are sent to the motor driver PCB. The motor driver PCB contains the DRV8701 gate drivers and external MOSFET H bridges. These circuits switch the battery power supplied to the motors and control both motor speed and direction. Power begins at the battery and passes through protection circuitry before being distributed to the rest of the system. A buck converter steps the battery voltage down to a level suitable for the ESP32 and other low voltage electronics. The load cell communicates through the HX711 analog to digital converter, allowing the system to measure cargo weight. For localization, the ESP32 communicates with the UWB anchors through SPI and I2C interfaces. These anchors interact with the user-worn UWB tag to determine positioning information. The CP2102 USB to UART interface allows programming and debugging of the ESP32 from a computer. From a hardware perspective, my primary focus was the power distribution path and the motor driver subsystem, ensuring that the ESP32 could reliably command the motors while safely handling the high current required by the drive system.
Slide 13, overall system schematic. Now I'll be discussing the overall system schematic for Scout. This schematic represents the integration of all major electrical subsystems into a single platform. At the center of the design is the ESP32, which serves as the primary controller and coordinates communication between the localization, sensing, and motor control systems. Power enters the system through a 24-volt battery and fuse-protected stage. From there, the power is distributed along two separate paths. One path provides unregulated 24-volt direct to the motor driver subsystem, which requires high current for motor operation. The second path routes power through a buck converter to generate the lower voltage rail needed for the control electronics. The ESP32 communicates with the DWM-1000 ultra-wideband module, which provides the relative positioning information needed for the cart to follow the operator. The control also interfaces with the HX711 analog to digital converter and load cell, allowing the system to continuously monitor payload weight. For user feedback, a 16x2 I2C LCD display provides real-time system information such as weight measurements and operating status. The motor driver circuitry receives commands from the ESP32 and converts them into the power required to drive the motors. Overall, this schematic demonstrates how the sensing, control, communication, and power subsystems are integrated into a complete autonomous cargo-following platform. Moving on to the next slide, I'll be discussing two of the key subsystems that make this integration possible: the power distribution network and the UWB localization module. Slide 14, power distribution and UWB module schematic. Beginning with the power distribution system, reliability and noise isolation were major design priorities. The battery output is split into two separate paths. The first path delivers unregulated 24-volt power directly to the motor driver boards, allowing the motors to access the current required during acceleration and operation. The second path feeds an LM2596 buck converter, which steps the voltage down to the regulated logic supply used by the ESP32 and other sensitive electronics. Separating these power paths helps isolate electrical noise generated by the motor for the microcontroller, communication modules, and sensory circuitry. This improves overall system stability and reduces the likelihood of communication errors or inaccurate sensor readings. The second half of this slide shows the UWB module schematic. This subsystem is responsible for determining the position of the user relative to the cart. An AMS 1117 regulator provides a stable 3.3 volt supply for both the ESP32 and the DWM-1000 components on the module. Communication between these devices occurs through the SPI interface, which provides the speed required for real-time ranging calculations. Additional reset and interrupt lines allow the ESP32 to manage module initialization and respond quickly whenever new ranging data becomes available. Together, these two subsystems provided the foundation for the project. The power distribution network ensures reliable operation of all electronics, while the UWB module supplies the positioning information that enables Scout to safely follow the user.
Shown here is the detailed schematic for one of the motor driver channels that I designed. The core of the circuit is the DRV8701 gate driver located in the center of the schematic. This device receives PWM and direction commands from the ESP32 and generates the gate drive signals needed to control the MOSFETs. Surrounding the driver are four CSD19536 KTT MOSFETs arranged in a full H-bridge configuration. The H-bridge allows current to flow through the motor in either direction, which enables both forward and reverse motion. To monitor motor current, the design includes a 0.01 ohm shunt resistor. This resistor creates a small voltage drop proportional to motor current allowing the DRV8701 to implement current sensing and protection features. The schematic also includes multiple decoupling capacitors and a large bulk capacitor connected across the 24-volt supply. These components help stabilize the supply voltage and reduce noise caused by motor switching. The fault-in output of the DRV8701 is connected back to the ESP32. This allows the controller to detect fault conditions such as undervoltage or overcurrent events. Additional protection is provided through the TVS diode connected across the power input. This component helps suppress voltage spikes generated by the motors and protects sensitive electronics from transient events. Also, a power indicator LED provides a quick visual confirmation that the board is receiving power. This design creates a robust motor control solution capable of safely handling the power requirements of our wheelchair motors while providing feedback and protection features.
Software selection and design. Now we'll get into the software side. This covers the language we picked, the development environment, the control algorithm, and how the overall system control flow works. Control algorithm selection. We looked at 3 options for the control algorithm. Pure Pursuit is built for following a pre-mapped path with waypoints. That's not really what we're doing. We're tracking a single moving person, so it adds complexity we don't need. Artificial potential fields naturally combines goal seeking and obstacle avoidance into one framework, but it can get stuck in local minima, and the computation is heavier than what we need on an embedded MCU. We went with PID control. The tracking error from UWB ranging feeds directly into the PID loop, and the output becomes the motor PWM command. The output also gets clamped by the load cell derived speed limit, so the 2 systems work together automatically. It's lightweight enough to run alongside all other free RTOs tasks on the ESP32. It also is the most practical to tune on real hardware, which matters a lot when you're working with actual motors and sensors. Programming language and environment selection. For the programming language, we went with C. It gives us direct hardware control, it's native to free RTOs, and it's the fastest option for the kind of real-time control loops we're running. Python and MicroPython were out early because the interpreter overhead creates timing problems for things like PMW and sensor reads. Arduino C++ wrapper makes setup easier, but it hides the free RTO control. We actually need to run everything at the same time. For the development environment, we chose Platform I/O inside VS Code. It supports the ESP IDF framework, handles library management cleanly, and it's the workflow the whole team was already comfortable with. ESP IDF standalone would have given us more low-level control, but the learning curve wasn't worth it given our timeline. The reason C and Platform I/O work well together for this project is that it gives us direct access to all the peripherals we need. SPI for the UWB modules, PMW for the motors, and I2C for the LCD. On top of that, free RTOs lets us run ranging, motor control, weight sensing, and display updates all in parallel without them blocking each other.
Now jumping to our software design, our system runs through 3 main phases. First is the initialization phase. On power up, the ESP32 verifies connections to the motor drivers, UWB anchors, and battery management system. It checks if the battery is above 10%, then it waits for a valid UWB tag handshake before doing anything else. If any of those checks fail, the status is displayed on the LCD and the system holds. Once the initialization phase is cleared, we enter location tracking. The ESP32 continuously pulls all 3 UWB anchors for the range measurements, runs trilateration to compute the tag's relative position, calculates the distance error, and feeds that into our PID controller. The PID output drives the motor PWM signals, speeding up or slowing down to maintain the following distance. The load cell reading is also factored in here to cap the speed based on payload weight. The last process is obstacle detection. We have 3 forward-facing ultrasonic sensors. If either sensor detects something within 2 meters, the cart slows down and self-corrects itself. If the sensor triggers, then the motor power cuts entirely until the path is clear.
Shown here is the motor driver PCB layout. One of the major goals of the layout was supporting high current operation while maintaining reliable switching performance. The red image on the left shows the copper routing and power distribution. You can see the very wide traces used for the 24-volt supply and motor current paths. These wider traces reduce resistance, minimize voltage drop, and help dissipate heat. The DRV 8701 gate drivers are placed close to the corresponding MOSFETs to minimize the gate drive trace lengths. Keeping these connections short reduces switching noise and improves overall performance. The large copper pores were added around the MOSFETs to improve thermal management. These copper areas help spread heat throughout the board and increase the effective cooling area. The board also includes dedicated locations for volt capacitors, decoupling capacitors, current sense resistors, and screw terminal connectors for battery and motor connections. A key challenge in this design was balancing high current routing requirements with maintaining clean signal paths for the gate driver circuitry. By separating power and control sections and using wide power traces, the final layout provides both electrical reliability and manufacturability. This PCB represents the final implementation of the motor driver hardware and serves as the interface between the ESP32 control system and the drive motors.
Slide 21, main PCB layout. Next, I will be discussing the main PCB layout. This board serves as the central hub for the entire Scout system and integrates the majority of the project electronics into a single PCB. The board contains an ESP32 microcontroller, which acts as the primary controller for communication, sensor processing, and motor control. In addition, the board includes interfaces for the HX711 load cell amplifier, the UWB localization module, the LCD display, and the USB to UART programming circuit. When designing the layout, one of the primary considerations was power distribution. 24-volt propulsion traces were routed using 80 mil wide copper traces to minimize voltage drop and reduce resistive heating. Parallel vias were also added whenever power transitioned between layers to maintain low impedance paths throughout the board. Another important consideration was noise isolation. The LM2596 buck converter and its associated inductors were positioned near the edge of the board to help reduce switching noise, coupling into sensitive analog and communication circuitry. Overall, this layout provides a compact and organized platform that supports all major system functions while maintaining signal integrity and reliable power availability. Moving on to the next section, I'll be discussing our prototyping and testing efforts, the results we achieved during the hardware validation. Slide 22, prototyping and testing. This section covers the hardware and software testing performed through Senior Design 1. Our goal was to validate each subsystem individually before integrating them into the complete system. Testing focused primarily on power regulation, load cell functionality, the UWB ranging performance, software reliability, and the system integration. Slide 23, hardware testing and performance. Beginning with hardware testing and performance, we first evaluated the buck converter responsible for powering the low voltage electronics. Under load conditions, the LM2596 regulator maintains stable output voltage with less than 50 millivolts of ripple, which is well within the acceptable limit for these digital electronics. We also verified efficiency and duty cycle performance using development hardware before transitioning to the final PCB design. Next, we tested the load cell and the HX711 interface. The load cell was tare calibrated and monitored using a logic analyzer. To reduce the electrical interference from the switching regulator, signal shielding techniques were implemented. After calibration, the system was also able to measure weight within approximately 1/4 of a pound of a known reference weight. At the system level, we verified that the 24-volt source could be stepped down within thermal issues and noticeable voltage snag during operation. We also successfully demonstrated end-to-end data flow from the load cell through the HX711 into the ESP32 and finally to the LCD display. Finally, UWB ranging performance was improved through antenna delay calibration. By adjusting the delay value using a fixed 1 meter reference distance, ranging accuracy improved to approximately 10 centimeters, meeting our project requirement. Moving on to the next slide, I'll summarize the software testing results. Slide 24, the software testing summary. Throughout Senior Design 1, a total of 13 software test cases were executed across the monitor control, load cell, and LCD modules. One of those 13 tests, 7 passed immediately, and 5 additional tests passed after debugging, and corrective actions were implemented. Only 1 test remains partially complete and will be refined during Senior Design 2. Several important milestones were achieved during testing. First, all 3 software modules reached a functional operational state. Second, the load cell achieved its target calibration accuracy of approximately 1/4 pound. Third, UWB localization consistently achieved approximately 10 centimeter ranging accuracy following calibration. Additionally, the LCD successfully displayed live weight data and system status information, confirming communication between the sensor and user interface subsystems. While testing was successful overall, several software issues were identified and resolved, which leads directly into the next slide. Slide 25, key bugs found and fixed. During development, 3 major issues were discovered and corrected. The first issue involved a free RTOS stack overflow. After the HX711 tear function completed, the ESP32 would repeatedly crash and reboot. Investigation showed that the floating point calculations required additional memory. Increasing the tack size from 2048 bytes to 4096 bytes completely resolved the problem. The second issue involved a timing conflict between the LCD and the HX711 load cell interface. The LCD communication occasionally interfered with the bit baying time required by the HX711, causing weight readings to freeze. The solution was to remove LCD updates from their separate task and instead use a free RTOS queue to pass data safely to the main application. The final issue involved calibration accuracy. Both the load cell and the UWB localization system required additional calibration to achieve the desired performance. After turning the load cell calibration factor and recalibrating the UWB antenna delay, the system achieved the required measurement accuracy for both subsystems. These testing efforts significantly reduced technical risk and provided confidence that the core hardware and software architecture is functioning as intended as we move into Senior Design 2.
Lastly is our administrative content. So this will include our budget, the work distribution, and our final steps. So first, going to our budget, we are looking at a total cost of $780 so far, which is a big difference from our original target of $400. And the main drivers for this big difference were the DC motors, the load cells, the motor driver, and of course the PCB fabrication and components. And this project is entirely self-funded by our team. And to manage costs, we have been reusing components where possible and borrowing equipment through the lab. And since the core electronics have been purchased, we are anticipating any more major additional spending. Moving on to our work distribution, work was divided based on our majors. So on the electrical engineering side, Sam handled the main PCB schematic and layout, the ESP32, the HX711, and the buck converter schematics, as well as the load cell implementation. Devani was responsible for the motor driver PCB schematic and all motor-related hardware. And on the computer engineering side, Cantrell led the microcontroller selection and the software design and implementation, and myself handled the UWB module selection and PCB design, and I also contributed to the software and managed our administrative documentation throughout the semester. As for the progress of our project, we are currently in 2 phases. The first one is PCB assembly and testing. So we are reaching the very end of assembling our PCBs and testing their functionality. We are also currently testing the PCBs of our current software to ensure the software works correctly with our PCB. And the next 3 final steps would be a full system integration and testing, where everything would come together for the first time in the actual flatbed chases. And that would next lead to our final assembly and documentation, and then the final presentation and demo, which will center on 3 highlighted specs: maintaining at least a 1 meter following distance via UWB, dynamic speed scaling based on payload weight, and a 15-pound payload capacity with live LCD readout. Thank you for listening to our presentation.